Okay, we're back. This channel is primarily about concrete house building. That's drifted off into a lot of things. And today we're going to talk about one of the most important things about a concrete house. That would be the reinforcement on the concrete, rebar, deform bar, call it a lot of things. But you need to know how much to put and where to put it. There's some not obvious things. We're going to start off with an example of not obvious things. You really don't have to have equal amounts of rebar in both directions. If you were building high-rise buildings and things like that, or your architect was really on top of latest technology or whatever, you're going to find that the most of the rebars are in one direction, and there's only perpendicular rebars enough to keep them spaced. I'm going to try to explain why that is if I can get the camera to go the other way. Of course not. Okay, I had to restart. What we're looking at here, if I can get it in front of it. I just drew this up. This is not a part of a house. This is just an aid to try to explain what's going on. What we have here is a rectangular frame. The scale is like 12 feet by 18 or something. Doesn't make any difference. Principle's the same. Now, my computer mouse is hung. Oh, I'm starting off terrible. I don't generally have that much problem with this. Okay. If we look at this thing from the side, you'll see that the center's depressed. And what it's trying to indicate is we've got two 2x4 frames with a piece of pretend rubber stretched between them. And the point of it is that if you press down some point on that, like you put your finger against the rubber and pressed it down, it doesn't just come down in one direction. All the directions come down. Left and right and up and down. They all get deformed. They all get stretched because the outside is constrained and the center is a continuous piece of rubber. So it all goes together. Now, the implication is probably not real obvious. If we put our reinforcements across this narrow span direction, right, it will receive a different strain. The stress will be the same, but the strain of this way is captured on a much smaller distance than the other way. So if you can restrain this direction, because this can become tight first. These are the ones that would break first if you go into the ultimate breakage on a rebar. So if we reinforce this narrow direction, there's a lot less stress is the load. That's the pounds of pressure you're putting on something. It's called other things, but that's the way I think of it. But it doesn't affect what you call it doesn't affect what it does. And when you put a stress on a material, and it has a yield point, and that's where when you release the pressure or the pounds, it springs right back to where it came from. So we have to work under that yield point. And so you have a certain 1,000 pounds per square inch on steel, 85 to 170. Rebars that fall between 96 and 101, around in that range. So what we're going to do is we know that we're going to get a higher loading over the shorter distance. So if we reinforce this direction, for it to stretch, it's also going to take all this other stuff with it, the ones that went in the long direction. So they won't receive as much strain, as much lengthening, stretching as the short one per unit of length. They only see half as much increase in their length as what the shorter distance does. So it's the determining factor. The shorter distance is the determining factor. The other ones, you have to have actually taken the shorter ones past the yield point and be headed for ultimate stress where it breaks. And it'll get there first. In every respect, it'll get there before the long ones. So, next item. We're going to try to get this thing on the screen. And what we're going for. We're going to analyze this this concrete and rebar several different ways. And because nobody likes to watch, well, nobody watches my videos anyway, I'm going to pretend there's somebody watching, okay? We're going to do first how you reinforce a suspended slab. That means that the slab is not sitting on the ground. It's restrained by either sitting on columns, or it's sitting on beams that are sitting on columns, or it's sitting on beams that are on grade, but it's hollow underneath. So that's a suspended slab. Now, there's two choices on the rebars. You have them running on the screen here, left to right, and then the little dots are, you're looking at the end of rebars that are running in and out towards you and away from you. So you'll notice that these left to right rebars are farther from the top surface. That means they're going to see proportionally more gain in length, more strain than these ones by a very small amount. But they will be strained first. They will get to ultimate tensile and break first. That's the first one that's going to break, is these ones going this way. Of course, we're designing so it doesn't break, but that's just the way it goes. So we're going to put our bottom layer of bars across a narrow direction of the slab. On our 12 by 18 or whatever, the thing we just looked at, that will be 12 feet. So I'm going to break this into several videos, because even though people don't watch my channel, I know that they don't watch them when they're over about 12 minutes long. I got 0 views on some videos because they're 30 minutes. So I'm gonna watch the clock here and seemingly cut in random places. Okay, so this is the first case we're gonna look at, is a concrete slab that's supported by the edges. There's two ways that you can have it. It can be supported on all 4 sides, or it can be supported on 2 sides. You know, like if you're looking at a hallway down through a house that's sitting on the walls, but there's a doorway on both ends and no beam, it's a flat ceiling, then it's supported only by the 2 long ones down the side. For our example, this is in centimeters. I drew it in inches, and then I multiplied it by 2.54, so it's scaled up. The scale doesn't make any difference. It's the magnitude of the numbers. So we're going to calculate it on inches, because I'm less likely to screw it up doing inches, since I'm in the U.S. As versus to being from Germany or wherever. Let's see. We have to have a few known things here. We're going to analyze this for a couple of different kinds of rebar. Number 12, that would be number 12 is the metric designation. Number 12 is the U.S. designation. I got that wrong. 12 millimeter is a number 4 rebar U.S. It is 1/8 of an inch. 4 1/8 is a half inch, and a half inch is close to the 12 millimeter. And the diameter of either one of them is 0.499. The square inches, you're going to need these things in calculations while I'm bothering with them. It's 0.195 square inches. A number 5 rebar, U.S., that's 5/8, is the same as a 16 millimeter. This is the diameter, that's the square inches. And this is the 1,000 pounds per square inches. And also you have to have the metric rating if you're going to calculate it metric. And I'd encourage you, if you work with a metric system, that you plug the metric things into the formulas, and you'll see you come out with the same number of bars and the same spacing, because they're basically the same bar. You're just using a different scale to measure them. I've only got the stress rating for the number 5. The number 5 rebar is 96 K means 1,000 per square inch, 96,000 pounds per square inch. The smaller 12 millimeters, which is basically a number 4 rebar, those are rated at 101,000 pounds per square inch. It seems odd that the smaller bar has a higher number, but the larger bar also has a much bigger square inches of area. So having more area, you have less circumference in contact with the concrete, and the amount of ribs, deformed ribs on the concrete per cross-sectional area is less. So it seems odd that you have 101 but this is compared to this is 1,000 pounds per square inch. So the actual strength of the bar is much higher because it's way bigger. It's almost, you know, it's 40% bigger than the number 12. So the pounds that the rebar will take is still higher. The reason that the difference on the per square inch is the surface area in contact with the concrete. So let's another item here. This is drawn up at 30 times the thickness. In US, it'd be 7 inches, or maybe I did this in 6. I'll have to look. Let's go ahead and look. We're going to be out of time on this first video before I even get it read. I know people don't like the computer, but okay, I do this up for 7 inches because this is what the suspended slab in Villa Cecilia is. We got a 7-inch floor. Actually, it's 8 inches at the center, and it's 6 inches at the outside. It averages 7. And because we run our rebar clear across the entire building, continuous, it doesn't go from one room and then start up at a wall and go to the next room. The rebars are continuous. The piece you cut off at the end of it starts the next row, so none of the seams line up. They're all staggered. Because of the this is the number 12 or a 12 millimeter or number 4 rebar. The distance between the bottom surface of the rebar and the surface of the concrete, called cover, is 3 rebars. Whatever diameter rebars you have is 3 times the diameter is the distance of the cover. That's so that it doesn't pull the rebar sideways and strip it and crack the cement. So that it can be farther, it can be closer to the center. Can't be closer to the outside. 30 times this, in this case, 7 inches of thickness. 210 inches is the maximum length between supports for this thickness of floor. It's 30 to 1. Now, you say, why is it? Somebody just thought that was a good number and stuck with it? Not quite. When you push down on a concrete, now this slab is designed to be pressed down upon. So the pushing down tries to make a curve. Well, I'm over here. I'm trying to make a curve, okay? So it's crushing the top together, and it's stretching the bottom apart, because that curve has a bigger radius to the outside, and pi times the diameter and all that. So top is in compression, the bottom is in tension. The compression strength of concrete for Villa Cecilia is 5,000 pounds per square inch. The tension is 1/10 of that, basic, real close to 1/10. So it's only 500 pounds per square inch. So where you get the 30 to 1 ratio is, once you put the reinforcing, this bottom surface can't stretch. It's sort of the pivot point of what's going on. So what you have, the limiting factor then becomes the top. Since you've taken away the 500 pound per square inch rating, all you got left to work against is this 5,000 pound up here. And if this is sort of the center of where you're trying to basically reverse stretch it from, then at what point do you crumble the rock and the concrete? When does it crush? And that's what determines the 30 times length to thickness. It's no harder than that. What do we have next here? I don't know if I'm going to be able to make this big enough to read. I can read it, though. That's not a problem. I'm going to have to read it. Let me get where I can see it. Calculation of rebars for suspended slabs supported on all four sides is done for the shortest of the two spans. Calculation of rebars for suspended slabs supported on two ends is done for the supported direction. Obviously, you can't hold it up from the part that's not supported. The fourth slab, or a beam, is assumed to have a top surface in compression and the bottom surface is in tension. And the loads are assumed to be equal. Otherwise it would be moving. The calculations are based on the moment of the mid-span weight from the top surface times half the span length. Okay? Calculation purposes. You take the worst case tension and compression, which is the middle of the beam or the floor. And if you stay with working with a single point there, and you tailored your method to the moments, then that's the place you want to take them. That's the worst case. That's where it would fail. So that's what you're going to calculate at that point. There's load in all of it, but that's the point. That's the highest, and what you have to counter with steel. The resisting moment is from the top surface to the center of the crossing direction rebars, because we're doing the crossing direction, because that's the shorter span. Okay. Resisting moment is from the top surface to the... Okay, that's telling you. In other words, you made a moment of half the weight of the slab onto the center of the concrete, and you figured that for the a moment. Length times a force is a torque or a moment. Years ago, we had that car engines that we rated bolt tightening in foot-pounds. A wrench a foot long, how many pounds would you pull on it? And of course, we had calibrated tools that were measured and verified all the time. 108 foot-pounds for head bolts on a dragster engine. And amazing enough, the main caps had more. Okay, we're going to use half the weight for our moment calculations in the center of the beam. The other half is assumed to be what's holding it up on the ends. And since your moment is the length times the weight, if you're measuring in the middle, you have a moment from the left end. That's half the span times the half of the weight that's there, because you put half of it on the supporting ends. That leaves half the weight divided between the left and the right moment. So you have 1/4 of the weight from the left, 1/4 of the weight from the right. And since you took it in the middle for your measuring point, the worst case place, you have half of the weight of the slab at the middle. And the lever arm is half span. It's from the support to the middle. So you multiply that length times that weight, you got, well, in the calculations, because there's so much of it inches, and they all have to have the same units, you converted everything to inches. And the only thing you have to convert is the half span, because everything else is per square inch or per inch or whatever. Okay. Okay, we've covered all that. There'll be two calculations for commonly used rebars of number 12 and number 16. The load-bearing rebars in Villa Cecilia are either 12 or 16. There are no there's some 18s, but they're in the 20 columns down at the bottom that hold the whole place up. But for everything else, floors and beams and everything, biggest one's 16, the smallest one's 12. The stirrups, that's the one that keeps the longitudinal bars from swelling out like a crushed marshmallow. We call them stirrups. And the stirrup is 1 bar size smaller than the long run bars. And that's consistent through the entire building on everything on it. So we're going to do number 12 and number 16. And I'd have to move this up so I can read it. I got a little thing here I made up. It's not a spreadsheet, but it works like one. Okay. We have 2 kinds of load that we have to hold up with these tension rebars. One is the dead weight of the concrete in the floor. That's the slab itself. This is the rock, sand, gravel, cement, sand, and gravel. Call that dead load. That's the building. It just sits there. It's not changeable. It's the building. And then we have called live load. That's the people walking on the floor, the furniture, the refrigerator, whatever you got up there. Have a party and you have a bunch of people. Well, somebody decided to have the standard, in the U.S. anyway, it'd be 50 pounds per square foot for things that are walking around on your floor. A dog runs across the room while you're having a party. Well, he's part of the weight. So we're going to do the dead load. Then we're going to do a calculation for live load. We add those 2 together, we have total load. And total load for calculation purposes is going to be multiplied by 1.5. And that's a safety factor. That's for when you have micro cracks in your concrete. You have something wrong with one of the rebars that was lapped over when it was rolled, and they didn't catch it and trim that out, It's just rolling defects. We don't have refining defects in carbon steel because the carbon is what you're refining out. Sulfur and carbon. Anyway, defects in the thing itself, and just peace of mind, for other reasons, we multiply by 1.5. Light aircraft utility categories, safety factor, I use a 3.8 for utility and 12.0 for aerobatic. Your commercial planes are 1.2 safety factor. They play it a little closer because the materials are held to a really high standard. And because you can only take a plane off and balance it in the air on that wing if the center of gravity is not between 19 and 31% of the width of the wing. You design for 25%. You get too much weight, which would overload the plane. It won't balance and won't fly anyway, so it doesn't make any difference. Obviously, I'm more interested in airplanes. I have to have a house. We're doing houses. So we're going to take some numbers and plug them into this sort of spreadsheet. 36 inches is the width that we're going to calculate for. Now, you're saying, oh, but wait a minute, your slab was 12 feet by 18 or something. That's true. And we don't have to have a 1/4 or 1/6 or 1/10 the width of the slab. What we have to do is have a meaningful size piece. I use 3 feet. The width of the slab, the short distance, 3 feet wide. The entire slab is going to have the same reinforcement. So what we do with that, we just continue on down the floor. So we've arbitrarily selected 3 feet. Books I've read when I was in college, that's what they used. I have no reason to doubt that it holds for the whole structure, so I use 36 inches. Everything else here is going to be what the building actually is. So the 36 inches of width times 229.6 inches of length times 7 inches of thickness. That equals 57,859 cubic inches. That's for the concrete in a 3-foot piece of the floor. That 57,850, I didn't put commas because it made it look like decimal points, so I'm having trouble reading it. 57,859 cubic inches of slab section across a narrow span divided by 1,728. That's 12 times 12 times 12. It's a cubic foot. And that, if you divide those, you'll get 33.48 cubic feet of concrete. The 33.48 cubic feet times 150 pounds per cubic foot equals 5,022.5 pounds of concrete. You take the 5,022.5 pounds of concrete divided by 2, the calculation weight, equals 2,511 pounds. The other half of the weight, the other 2,511 pounds, is sitting on the supports on the end of your strip. That's another reason why I use a strip. It takes dealing with the long spans that aren't supported out of the equations. Doesn't change the result. It just takes away several pages of math. So half the weight is on the ends. 2,511 pounds is your load. Now, we have to have a live load calculation, and we have to keep the computer going. Come back. Same 36 inches of width times 229.6 inches of length equals 8,266 square inches of surface area. 8,266 square inches of area divided by 144 square inches per square foot is 57.4 square feet. 57.4 square feet of surface area times 50 pounds per square foot. It's a live load of 2,780 pounds of live load. We add the 5,022.5 pounds of dead load plus 2,780 pounds of live load. It's 7,802.5 pounds of total load. 7,802.5 pounds of total load times the safety factor, 1.5 in this case. 11,704 pounds of load. 11,704 pounds of load times the inches of span divided by 2. Okay, so that's, what was it, 6 feet? 12 foot would be 6 feet. It's a moment of 1,343,591 inch pounds. 1,343,591 inch pounds at half the span length. Okay, that's the moment that you have to be able to hold with your steel rebar. So what we're going to do is we're going to take the 1,343,591 inch pounds, and we're going to divide that by how far the rebars are below the top surface. Okay, here's our rebar, and there's our top surface. So it's 5 1/4 inches. Now, if you add that to the 1 1/2, you get 7. It's not right. 5 oh, okay, yeah, it is. Because the rebar for cover is measured from the bottom surface of the rebar, and we're measuring to this center of a 1/2 inch piece, so it does come out. Because you would take the 1/4 inch away. Okay. The rebar is being strengthened here at the bottom, and it's trying to make it crush the top. So we're going to do the calculations for the resisting mode from the top surface, because that's the point it would fail at. So if we have the total moment, the new lever arm for the steel is from the center of the rebar. You only use the rebars closest to the bottom. You can't strain the other one anyway, but you take it from the center of your rebar to the top surface, because we're trying to make this at the bottom, just as strong as what it takes to crush this. We're making it only what it has to be, because we added a 1 1/2 safety factor. Now let's see if we can get back to where we were. Okay, I've already run past where I was supposed to for the first video. I'm not quite ready to do a part 2. Let's just finish this one little part here. And we haven't got it on the screen. Oh, I think we're close to getting at what we're supposed to be looking at. Okay, 1,343,591 inch pounds a moment at the half span distance, and we're going to divide that by 5.25 inches. And that's going to give us the tension load, the amount of pounds, actual pounds that is, the rebar has to resist. Because the moment is a length times a weight. So we just did it the same thing, and we come up with, because we divided it by the by the dimension down, that gives us back to pounds. So it's 255,922 pounds of load. This apparently is for a number 12 rebar. And the pounds of stress rating for a number 12 rebar is 101,000 pounds. It's written in the books as K101. And that equals, farther on the left here, 253 square inches of rebar. If we take the 253 square inches, and then we take one 12 millimeter rebar, has a diameter of 0.195 square inches. So we've got the square inches we need. This is square inches of a bar. So we divide the square inches by the square inches in a bar. We come out with, off the end of the screen here, of course, 13 bars. And that's rounded up to 13 from like 12.77 or something. If it was 12.2, really close to 12, you're still going to round it up to 13. Anything less is underdesigned. And what you're trying to do with this video is find out if your architect's got it reasonably close. He may use a... I'm sure there's other ways other than the way engineers do this, but people that don't design airplanes have probably got some kind of architectural way of doing it. Now, we're going to find out how far apart the bar spacing has to be. We have a 36 inches of width. That's all the numbers are from. We have 13 bars over here. And if you divide 36 by 13, you get 2.77 inches. Now, that's really close. You ought not to ever be under like 3.5 or 4. Probably 4 would be a good minimum. I use 4 on Villa Cecilia. If it comes out to 3.9, let it go. If it come out to 6 and needed to be 4, then I'd have made it 4. And that's important on beams more than floors. Now we're going to look at the spacing for the bigger number 16 bar. Same pounds of tension load. This time the stress rating is not 101,000, it's 96,000. Comes out to 2.67 square inches. You notice it's very close to the 2.53 square inches. 2.53 went up to, or down, up to 2.67 because the load rating on the bars is slightly lower. So if we take the square inches of 2.67 over here, off the screen, of course, and take the area of one 16 millimeter rebar of 0.307 square inches, that's the number of bars required. That's 8.66. It rounds up to 9. So you have to have 9 bars. So 36 inches of width times 9 bars comes out to a spacing of 4 inches. Now you remember, we're holding up a 7-inch thick floor. If this was a thinner floor, or if you took a 1/2 inch off of your cover on the bottom for a smaller bar, because the diameter of the bar is not as big, it's still 3 bar diameters from the bottom. This thing could get up to 8 inches, but on our case, on Villa Cecilia, it's 4 inches. We've poured that floor with a 7-inch spacing. The reason is that we're nowhere near the 30 thicknesses on a room size. And also, we didn't run the bars straight short wall to short wall and long wall to long wall. We ran them across the building, which is, for all intents and purposes, round. And they run continuous. So basically, they're mostly at an angle, like 45 degrees to the wall, in which case there is no short length. And you basically can count all the bars rather than only half the bars. And you got to remember, these calculations are for